All right, today we're going to go over mathematical mathematical induction. Give you a fair warning right now. You are going to hate the lesson. You are going to think it's super difficult. But once you get the hang of it, it's really not bad. Promise. You're just going to think it's horrible at the beginning. Okay, so mathematical induction, it's a common method of proving that each statement of an infinite sequence of mathematical statements is true. The principle of math induction contains both English and math steps, and there's 3 steps to them. You have to include both the English and the math in order for it to count. You will lose points if you don't include the English statements for each of the steps, but it just follows the same pattern every time. We're going to let Pn be a statement involving natural numbers. And then step 1 is to prove that P1 is true for n equals 1. And then you'll actually show, so you'll make that English statement, and then you'll actually show mathematically that it works for when n is 1. Step 2 is going to be to assume that pk is true for when n equals k. And there's no proof on this step. You'll make that English statement, and then you'll just state the pk statement. You'll plug k into all of the n's, and you'll just make the statement. And then step 3 is you're going to prove that this is true for when n is equal to k plus 1. And this statement, you're going to start with step 2, you'll repeat step 2's line, and then you'll work off of that. And then your conclusion that you will write in English words is, by mathematical induction, the above statement is true for all natural numbers. Let me go back. Go ahead and just pause it if you still need to write down this slide. Pause. And welcome back. All right, so let's do one. Example 1. We're going to use mathematical induction to prove that the sum of the first n odd positive integers is n squared. So here's the first n odd positive integers, right? So 1 plus 3 plus 5 plus ... And if you remember, 2n minus 1 is a way to write an odd number, right? When you plug in a 1, for n equals 1, you'll get 1. When you plug in a 2, you'll get 3. When you plug in 3, you'll get 5. And what we're saying is we want to prove that the sum of these n odd integers ends up being n squared. Okay, so here's the math induction proof. You start off by, you literally write Roman numeral 1. Prove that P1 is true for n equals 1. This is literally plugging in a 1 into n here and showing it's true for n squared. I mean, I cheated a little bit and I just went, okay, the first term was just 1. You could have also went 2 times 1 minus 1. Is it equal to 1 squared? And sure enough, it is. And so, boom, there you go. I did all that, but really, here's what I would do. If I was doing it by hand, I would go 2 times 1 minus 1. Is it equal to 1 squared? And this would be 2 minus 1. So 1 and 1 squared is 1. Check. That's really what my work would have been for that. I showed a bunch of extra steps that I don't know why I did that, but that's what I would be looking for. Okay, so we just proved that it's true for when n is 1. Your next step is you write in words, assume that pk is true for when n equals k. And this is 1 plus 3 plus 5 plus, notice what I did here. They gave me this statement in terms of all n's. This step 2 is just replacing the n's with k's. Replace that n with a k, replace that n with a k. That's all you're doing on step 2. You're assuming that this statement is true for when n is k. All right. Then, step 3, you'll write in English words, prove that pk plus 1 is true for when n is equal to k plus 1. Now this, you do not just plug k plus 1 into n. No, no, no. Do not plug it in. Instead, you're going to start with statement 2 because we've assumed that this guy is true. And then we want to do things to that statement to then end up with a conclusion that, okay, when n is k plus 1, then it's also true. So you do not plug in k plus 1 into n on step 3. You do plug k into n on step 2, but don't plug it into step 3. So notice what I did. All I did here, I rewrote the exact same step from step 2. Right? I've got this. We assumed it's true, so I'm saying this is a true statement. Then, for this type of problem, what you're going to do to show that it's true for k plus 1, k plus 1 would be the very next integer, right? So what you're going to do is you're going to take this whole left-hand side, write it again. So look, 1 plus 3 plus 5 plus dot, 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 plus 2k minus 1. And then what I did was I added the next term to the left-hand side. Now I'm plugging in the k plus 1 into n, right? 2k plus 1 minus 1. And then is that equal to the k squared here? What I added to the left-hand side, so this is what I added, was the very next term. And then I just added the exact same thing to the right-hand side of the equation. Remember, we've got an equation here, so as long as whatever you add to the left, you add to the right-hand side also, it's still a true statement, right? And on the left-hand side, I added the next term, and the next term would be when you plug in a k plus 1 into this n. Just don't plug in a k plus 1 into n squared, right? That's what our conclusion will end up being. We should end up getting that this ends up being k plus 1 squared, right? So you're adding the next term, do it to both sides. And then this left-hand side is golden. That's exactly what we need. But the right-hand side, I need to simplify this. And if this statement is true for k plus 1, then that means that this right-hand side will simplify to be k plus 1 quantity squared. All right, so let's do some simplifying. Distribute that 2 to the k and to the 2. Yeah. Ooh, that's some weird notation, but okay. We want the right-hand side, RHS, I mean right-hand side, to end up equaling k plus 1 quantity squared. That's what we want. It's not what I plug in. All right, so I distributed the 2 times k and 2 times 1 to get 2k plus 2 minus 1. Well, 2 minus 1 is just 1, so this simplifies to k squared plus 2k plus 1, which, by the way, factors as k plus 1 quantity squared. We just proved that it's true. That was what we wanted. We want our final answer on this right-hand side to be if we had plugged in a k plus 1 into n. Yeah. All right. Then the last part that you put is by mathematical induction, the above statement is true for all natural numbers. And then mathematicians like to write QED as meaning the end of the proof. In Latin, it means quod erat demonstratum, which means which had to be demonstrated. You asked me to prove it. I just did. It's kind of like the final mic drop. Oh yeah, I just did it. You asked me to, and I did it. That's what a QED is, basically. All right, one other thing that I'll just point out is that the way math induction works is, remember, we proved it was true for when n equals 1, right? We assumed it's true for just when n equals k, and then we proved that if it's true for n equals k, then it certainly is true for n equals k plus 1, right? So what that means is it's like a domino effect. I proved it's true for n equals 1. I've also now proven that it's true for k plus 1. So if it's true for 1, then it's true for 1 plus 1. So it's true for when I plug in a 2. And then it's true for when I plug in a plus 1, 3. It's true also when I plug in a 4, because it's like a domino effect. If you proved it's true for 1, then you just assume it's true for just any value of k, any positive integer, right, a natural number. you assume it's true for whatever number, doesn't matter. Then we said, okay, if it's true for k, we just proved it's also true for k plus 1, which just means if 1 is true, then it's true for 2, it's true for 3, it's true for 4, it's true for all natural numbers. So that's how math induction works. You'll prove it's true for 1, assume it's true for just a random k, and then from that, assuming it's true, prove that it's true for the next guy. Okay, let's do maybe another one, I think. Yes. All right, so this type is done differently. And you're going to hate it. Okay. Use math induction to prove that 4 to the power of n minus 1 is divisible by 3. The first step is we're going to prove that P1 is true for n equals 1. Include that English statement. All right, let's prove it's true. All right, so when you plug a 1 into n, you would get 4 to the power of 1 minus 1. And we want to know, is this divisible by 3? Well, that's equal to 3, which is definitely divisible by 3. And so, yep. We assume pk is true for when n equals k. So now you write 4 to the power of k. You're replacing this n with a k. We say it's divisible by 3. Now, in math language, how is that written? Because we don't always write out these words, right? We got to do math to it. To be divisible by 3 means that your whatever this ends up equaling, whatever number it is, it's 3 times some number, right? Where that number must be an integer. Right? It has to be an integer because otherwise it doesn't make sense, right? It's not 13 is not divisible by 3 because to be divisible by 3 means that it is a multiple of 3, right? So it could be integer means it could be a negative or positive, right? But it's not a fraction. It's got to be either 3 times 1 or 3 times 2 or 3 times 3. Those are things that are divisible by 3. So this is how you state in math language, right, that 4 to the power of k minus 1 is divisible by 3 means that it's equal to 3 times t, where t is an integer. All right, now we're going to prove that it's true for when n is k plus 1. Remember, we start with step 2, so I'm going to rewrite this guy exactly like that. I should have written where t is an integer, but I guess because I just wrote it right there. All right. How do we do this one? Well, I need 4 to the k plus 1 now. I want 4 to the k plus 1, and then minus 1 is equal to 3 times some integer. It's not going to be the same integer that this t is, right? It should be something else. Yeah. So, what would it? Okay. So I need my left-hand side to be 4 to the power of k plus 1. So how am I going to get that? Well, if you remember properties of exponents, that 4 times, do you agree that if you do 4 times 4 to the k, you would have, by properties of exponents, write it, if I have 4 times 4 to the power of k, this is like 4 to the power of 1, same base, keep the base, add the exponents. You agree? By multiplying by 4, I'm going to get 4 to the k plus 1. So, but I can't just multiply the 4 to the k by 4. You have to multiply the entire left-hand side. And then if you do that, you have to multiply the entire right-hand side by the same thing. This is an equation. I'm allowed to do something to that equation as long as I do it to both sides of the equation. So, multiplied both sides of the equation by 4. Then you'll distribute this 4 times 4k, which will give you 4 to the k plus 1, and then minus 4 times 1 will give you minus 4. All right. And then 4 times 3t would be 12t. Okay, now keep in mind, we are trying to prove that 4 to the n minus 1 is divisible by 3. I need a minus 1 here. I can't have a minus 4. I need a minus 1, right? I need this left-hand side to be 4 to the k plus 1 minus 1. So what am I going to do? I'm going to add 3. And as long as I add 3 to the left-hand side of the equation, you want to add it to the right-hand side as well. So 4 to the k plus 1 minus 1 equals 12t plus 3. My left-hand side is perfect. That's what I need to show to prove that it's true for k plus 1. Now I just need the right-hand side to be 3 times something. Well, let's factor out a 3. So 3, factoring it out, I'm left with 4t plus 1. Yeah, and that's true. Since remember, t was an integer. And if you take an integer, right, and you multiply it by 4, it's still an integer. And when you add 1, it's still an integer. So that's enough. And then you do your conclusion of by mathematical induction, the above statement is true for all natural numbers. Booyah! Drop the mic, right? All right. I know it's weird. It takes some getting used to, but it is very procedural, right? I'm not done, so don't stop the video because we're going to do a problem together. But I have it on here, so I might as well go through it again. All right, so your homework is this, guys. Make sure you also add these 2 problems you want to show because your book didn't have this divisible by and divisible by, so do a couple extra of those. Don't forget, remember your laws of exponents. If you're doing 3 squared times 3 to the 4th, it's 3 to the 2 plus 4, and so 3 times 3 to the k is 3 to the k plus 1. Also, keep in mind that also means 3 times 3 to the k plus 1 will give you 3 to the k plus 2 because you're adding a 1 to that guy. And so for extra practice, let's do a question together. I would love for you to pause the video like through it and try to see if before I tell you what to write that you can do it. Maybe. Fingers crossed. Oh, it's a doozy. Okay, this is homework number 12. Is that one of the ones you had to do? Yep. Okay, so this is the first problem of your homework. So maybe you want to get out a paper, right? Start your homework with me. Okay, we want to use mathematical induction to prove this statement is true for all positive integers n. So we got 1 squared, 2 squared, 3 squared, all of that. Okay, so yeah, this is a doozy. It's a good thing we're doing this together. All right, but you should know how to write step 1, right? Step 1, English statement first. Prove that P1 is true for n equals 1. So I would show when I do a 1 on the left-hand side, I would have 1 squared and then plug a 1 into all of these n's. Let's see what I show on here. Really, you should write a question mark right there. It's what you're trying to prove, right? So I'm going to add in a little question mark. This is what I would write when I was proving question 1. Is 1 squared, which would be if you plugged a 1 into n here, equal to plugging a 1 into n here, a 1 into n here, and a 1 into that n there. All right. Well, the left-hand side is 1. Over here, you got a 1 times 2 times 3 over 6, which is definitely true. All right. Can you write step 2, the English words? Remember, step 1 is a prove, and step 3 is a prove, but step 2 is an assume. Assume that PK is true for when n equals k. And that is literally taking this first statement that they gave you, and when you see an n, you're replacing a k with it. I know that seems weird to you, but in math, this is what we do. I'm just saying k is some random natural number in that line, right? It's not 1. I mean, it could be 1, right? But it's some other number in that line. So just in general, but we change it to k so that it's not the same as n. All right, so see, I wrote, make sure you write up, don't just write k squared, because that's not true. It's the sum of all these numbers that's equal to this. So you need the 1 squared plus 2 squared plus 3 squared plus ... plus k squared. Without all of these guys, you're wrong, because k squared is not equal to all of this. No, it's the sum of all of these numbers that is equal to that. Okay, so that's step 2. Step 3, can you write the English words? It's prove that pk plus 1 is true for when n is k plus 1. And remember, the first step is just to rewrite that same statement from step 2. I rewrote it. I know it's a pain. You guys hate writing things down, but that's what you got to do. Repeat the whole thing, including the 1 squared plus 2 squared, all of that. You got to include it. Don't leave that off. Okay. I want to prove it's true for k plus 1. Whenever it's like an adding the next term type of thing, then that's when you add the same number to both sides. The divisibility one is when you multiply both sides by that number to get the k plus 1. But here you're going to just add the very next term. And the very next term on the left-hand side would be a k plus 1 quantity squared. So you add a k plus 1 squared to the left-hand side, and then you're adding the exact same value to the right-hand side. Notice I have not plugged in a k plus 1 into all of these guys. That's what I'm going to end up proving is true, that when I simplify this right-hand side, that I will get that. Do I show what you need? Yep. Okay. My left-hand side is perfect. It's exactly what I need to show. My right-hand side, what I want in the end, I want my right-hand side, RHS, right-hand side. I want it to be instead of this k here, I want it to be a k plus 1. Instead of this k here, I want it to be a k plus 1. Instead of this k here, I want it to be a k plus 1. So that's what I want it to be. I'm going to simplify it just so that way you can see that, I'm going to simplify it right here just so that way when we start simplifying this side, you'll be able to see, oh, look, I got it, right? Okay, so a k plus 1 is a k plus 2, and a 2k, a 2 times k plus 1 would be 2k plus 2 and then plus 1. So that simplifies to a k plus 1, a k plus 2, and a 2k plus 3 all over 6. So that's how I'll know that I got my right-hand side perfect. All right, I'm adding this guy to this right-hand side. Well, in order to add it to a fraction, you need a common denominator. So I multiplied top and I put this like over 1 and multiplied top and bottom by a 6. All right, so that way I got a common denominator. Yeah, so that's all that is. Okay, now here's the little tricky trick. I know I need one of my factors to be a k plus 1. And do you see that I have one in this term? You know, this whole thing before the plus sign is one term, right? And I've got a k plus 1 there. I also have one here. I actually have k plus 1 times k plus 1, but I have it there. So I'm going to, hopefully that's what I do. Yes, good. I'm going to factor out the k plus 1 that these two terms have in common, because I need one right there. It'll just help you out. Otherwise, you're making a cubic, like you multiply them all out and do a cubic, and then you'd have to factor it, which is a pain. It can be done, but it's a pain. Versus if you see one of your factors that you need already sitting there in both terms, then factor it out. Okay, so I factor out a k plus 1, and I would be left with, in the first term, it's a k times 2k plus 1. And then in the second term, it's a 6. And then remember, one more of these k plus 1s. And then all over 6. I combine them into the same numerator. All right, now let's go ahead and distribute this k into both of those guys. And distribute the 6 into both of those ones, so that I still have this k plus 1 times, and then 2k squared plus k plus 6k, so that's where I'm getting the 7k, and then plus 6. And then this guy is going to factor. Now, hint, if we did everything right, it should factor as k plus 2 times 2k plus 3. Is it? Let's see. 2k squared, boop, boop, plus 3k plus 4k would give me plus 7k, and then plus 6. So it does factor that way. And then, of course, I show the actual, like, you know, this step was that step, and so then this step is my final step down here where I'm showing all of the k plus ones in there. Then I can put the check sign and go, yep, I just proved it. I proved it's true for k plus 1. And then your conclusion is, by mathematical induction, the above statement is true for all natural numbers. Booyah! Drop the mic, right? QED. Okay, I think that's it. Yep. All right. No, I do not want my annotations. You all have a fantabulous day, and come see me in office hours. I'm sure you're going to have lots of questions on this one. Yeah? I think so. All right, you guys have a good one. Bye.